Hello, my name is Max Munson, and I am a student of the University of Alabama under the mentorship of Dr. Red Wahidi. Along with my co-authors Alex Alberson and Kasana Zuckerman, I studied the effects of vortex interaction on propeller performance. I would like to begin by thanking the University of Alabama and the National Science Foundation for providing funding and use of resources for our research. So the inspiration for this research was urban air mobility vehicles, or UAMs. These are essentially small electric air taxis, and they promise to be a quicker and more environmentally friendly mode of transport. However, first they must overcome the challenges of the urban environments in which they operate. And this includes susceptibility to large-scale vortices because of their small size, and a need for greater control authority and predictability due to their low flight speeds. So some of the previous research that has been done in this field has studied the movement of vortices through the propeller plane, in which it's been noted that they move radially inward and in the circumferential direction of propeller rotation. In addition, it has been noted that the tangential velocity component of vortices has the largest impact on propeller performance. So this led to the hole in our research that our research question hoped to answer of what are the effects of large-scale vortices with different rotational directions on downstream propellers? And we were hoping to get some experimental data to study this. So our hypothesis was that a counter-rotating vortex, or one that moves in the opposite direction of propeller rotation, would create an increase in both thrust and torque, and that a co-rotating vortex would have the opposite effect. Using the simple coefficient of lift and drag equations, we can see that coefficient of lift, coefficient of drag are all going to be based on your propeller geometry. Your changes in density are going to be relatively small at the low speeds in which we were testing. So we would expect that with an increase in velocity, we would also see an increase in lift and drag on the propeller. So here are two schematics of our experimental setup. We had a Hotwire anemometer mounted on a 2D traverse. We had a load cell in between our motor and our motor stand. And then in front of all of that, we had a 6-inch stand, 6-inch cord NACA 0018 airfoil that we used to generate a tip vortex. And by changing the orientation of this wing, we could get different rotational directions. So in order to cut down on time looking for the initial, or doing our initial surveys to find where the vortex was located, we used SolidWorks FlowSim, and we found that it did actually provide relatively accurate data for the size and location of our vortex. So to experimentally get the data for where our vortex was located, we, in our subsonic closed circuit wind tunnel, we used the 2D traverse with the Hotwire to locate the tip vortex generated by the NACA 0018 wing. And we used this plot on the bottom left where we took it at multiple streamwise locations in order to figure out where we had the most coherent vortex. And then after that, we decided where was the most coherent vortex. We used the top right plot in order to figure out where the center of the vortex was located. And as can be seen on these bottom two plots, this is after we put the propeller in the wind tunnel. We can see that the vortex is slightly to the right of the motor. So we have relatively good accuracy of predicting where the center of the vortex will be. For the purposes of our testing, we used 8x4, 8x6, 9x4, and 9x6 propellers, and this allowed us to control for both the diameter and the pitch of the propeller. And in this case, the first number is going to be your propeller diameter in inches, and the second number would be your propeller pitch in inches. We also got some initial thrust estimates using the conservation of momentum, the MATLAB code we developed. The green dots are going to locate a place where U, or the local velocity, is measured, and the red dots will be anywhere where the free stream velocity was measured. And from this, we can see relatively good matching with our hypothesis that a counter to rotating vortex would increase the coefficient of thrust, and a co-rotating vortex would decrease the coefficient of thrust. So for our experimental procedure, we started by setting the wing angle and propeller stand location. We used a speed of 22.2 miles an hour, which roughly corresponds to 10 meters per second. For the first data set, we would set the propeller to the minimum possible rotational frequency where it wasn't just windmilling. And then after that, we would take 20 force and torque data points in 3 dimensions, and we would then increase the rotational frequency by 500 RPM as measured by a photodiode. And we would repeat steps 4 and 5 until 2 or 3 points passed where the thrust reversed. So for our data on all of these plots, I'm going to have the advance ratio on the x-axis and the coefficient of thrust or coefficient of torque on the y-axis. So we did find that, in fact, the counter-rotating vortex did indeed increase both the thrust and torque applied to the motor, while the co-rotating vortex decreased the thrust and torque applied to the motor. As for how the propeller geometry affected the thrust, we can see that by comparing the 2 plots for the 9-inch propeller, which is going to be those 2 on the bottom, we can see that an increase in diameter caused a very small increase in the effects of the vortex. If we look at the 2 6-inch pitch propellers, which are going to be the 2 on the right, we can see that the pitch caused a much more significant increase in the vortex effects. For torque applied to the motor, we can see that increase in diameter actually appeared to cause a small decrease in the vortex effects. Especially, you can see that in the 8x4 and the 9x4 data, which is going to be the 2 plots on the left. And for propeller pitch, we can use the 9x4 and 9x6 plots to demonstrate that the increase in pitch caused a relatively significant increase in the torque applied to the motor. And those are going to be your 2 plots on the bottom. Now, there are some limitations to our research I'd like to acknowledge. For instance, based on environmental factors or the rotational frequency of the propeller, there was some relocation of the vortex. However, we have reason to believe it did hit the vortex or hit the propeller in every case. There's also some uncertainty in the y-axis, as can be seen in this right plot, due to the fact that we used a one-dimensional Hotwire. Finally, there were some minor free stream velocity abnormalities throughout the test area of our wind tunnel, which can be seen in the bottom left. However, these never got above 1% of the free stream velocity. In conclusion, it is my hope that this research could lead to the creation of improved small aircraft stabilization systems and be used, the data points could be used as a comparison for CFD modeling. Finally, some ways this research could be extended in the future would be to determine if these specs are the same on some alternative propeller geometries, for example, toroidal propellers, or the determination of numerical models for predicting vortex-propeller interactions. Here are the citations I used for this presentation, and I would now like to open the floor to any questions.
Any questions?
What was the reasoning for the selection of the size of propellers, like you were going over?
It was mostly based on what we already had, and like I said, we wanted to pick 2 propellers with the same pitch and 2 propellers with the same diameter at least. But other than that, it was based on what we already had at the university.
You mentioned that increasing the pitch had a greater effect on the vortices. Do you attribute that to like greater separation, or what mechanism do you attribute that to?
Were you referring to the torque or thrust data sets?
Right.
We have not done enough research because we only had 1 semester to do this research, but I would like to in the future possibly continue this research to study what is the actual cause of this increase.
Any other questions?